let's start with a nice clear diagram of what's going on. We've got a non-uniform plank and it is on two supports, P and Q, like this. So this is P, this is Q, this is A, this is B, and we know that A to P is 2D, and we know that A to Q is 4D, but the whole thing is 5D, so this must be D here, leaving us with 2D in the middle. It's a non-uniform plank, so I don't know where the mass is going to be, the centre of mass, so I'm just going to put the weight coming out of a random point which I'll call X. That means that from P to X is little x, because I don't know how long it is, and from X all the way over to Q will be 2D minus X. Okay, what else do I know? A particle, oh, I know the mass, 8m. Do I have to put mg? I know the mass. 8m. Oh, I know there'll be a reaction at P and another reaction at Q. Anything else? A parcel is placed on the plank at B. So here's our parcel. This is B at the end here. And the particle has got mass. Oh no, I do need a G. What am I talking about? 8m. 8mg. The mass is 8m. So the weight is 8mg. The mass of the particle is 6m. So the weight of the particle is 6mg. And we're modelling the plank as a rod, which means it's not going to bend, and the parcel as a particle, and so that means its mass is just going to come out of the point that I've drawn on. It comes out of a point. Calculate the distance of the centre of mass, that's where I've put X, from A. So the question is asking me basically what 2D plus X is. That's what I need to know. So here's a picture of what's going on. Oh no, I missed something. The plank is on the point of tilting about Q. Oh, that's really helpful. Okay, if it's on the point of tilting about Q, then basically, if you imagine this point here at Q, it's about that particle at B must be so heavy that it's literally just about to lift off P. So actually, it's really, we can model it as not touching P at all, because it's tilting about Q, so it's just a millimetre taken off at P, so nothing's going on there. So, well, to be honest then, in that case, with my picture, rather than having 2D and then X, I might do these lengths a bit differently, because essentially there isn't even a pivot there. So I think I might label this differently. I think it's probably going to make the calculations a bit easier. So we know that, what do we know? A to P is 2D, but that's not relevant anymore because P isn't featuring. So I'll call that X, and then the whole thing is 5D. So from A to Q is 4D, so this bit will be 4D minus X. Oh, that looks much nicer. I like this now. Okay, I'm ready to go with this. Okay, top tip when you're doing moments and you've got like a seesaw type situation, because the plank is in equilibrium, all the forces up are going to be of the same magnitude of all the forces down. Now this may or may not be useful, but if you always start with it, then you've got a little equation sitting there, and if you need it you can go and take it, and it's the sort of thing that people forget to do. So if you just always do this first, then you'll get into good habits. So R, that's all the up forces, equals 8mg plus 6mg. So R equals 14mg. Now I'm not saying that is going to be useful, but I'm just saying just do it, leave it sitting there, and then if you need it, it's there for you. And if you don't, well, it only took a second, so it's not a big deal. Okay, let's do our moments. Where should we take moments about? We could take moments about A or X or Q or B, doesn't really matter. I will choose A. Why not? Moments about A. Okay, so we have got the 8 mg force, and that is going to rotate clockwise about A. And we've got the 6 mg force, which is also going to rotate clockwise about A. And then we've got the R force, the reaction force, which is going to rotate anti-clockwise. So this one will be, the RQ will be on one side of the equation, and the other two will be on the other side of the equation, because they're balancing, because it's an equilibrium. So the moment of the force 8 mg is 8 mg times perpendicular distance to the pivot, which is x. And then we've got 6 mg, and the moment of the force 6 mg is the magnitude times the perpendicular distance to the pivot, which is 5d. And on the other side, we have got the force R, and its moment is its magnitude, which is R, times perpendicular distance to the pivot, which is 4d. And actually, I know that R is 14 mg, because I did that a minute ago. So I can put all this together. So I've got 8 mgx plus 6 mg, actually 6 times 5 I can do, 30 mgd equals 14 mg times 4d. So let's cancel mg off everything. See what we're left with. 8x plus 30d equals 56d. Is that 4 times? Yes. So 8x equals 26d, so x equals 26 over 8d, which is 13 over 4d metres. And that's the distance of the centre of mass from A. But you could have taken moments about any point. It would have worked regardless of which point you've chosen to take moments about. So just to prove to you what I said about the point that you choose to take the moments about, I'm going to show you what would happen if I'd chosen another point. So I'm always going to start with up is down. Always, always, always. R equals 8 mg plus 6 mg. Might not be useful, might be useful, why not just do it anyway? Now I'm going to take moments about x. Now about x, if we're taking this as the point we're taking moments about, there's only two forces that have a moment, because the 8 mg is going through that point, so it doesn't have a moment about that point. It doesn't cause any tilting. So we've got the R going anti-clockwise, and we've got the 6 mg going clockwise. So on one side of the equation, 6 mg. That, to make the moment, we multiply that by the distance, which is 5d minus x, and that equals the R, which is 14 mg, which we got at the top, multiplied by the distance to the pivot, 4d minus x. So that's 14 mg, 4d minus x, and let's see what happens now. 30 mgd minus 6x mg equals, what's that, 56 mgd minus 14 mg. And let's cancel those mg's off everything. Let's see what we're left with. Just realised I dropped an x. 14 mg times, there we go, 14x. So I've got 30d minus 6x equals 56d minus 14x. So if I put my d's on the right hand side, that's 26d's, and if I put my x's on the left hand side, that's 8x's, and obviously I'm going to get the same answer. Equals 13 over 4d metres. Okay, let's try one more. Guess what I'm going to start with? I'm going to start with up equals down, because I'm always going to start with up equals down, and I'm never going to forget to do that at the beginning, just in case it's useful. So there we go, up equals down. Now I'm going to take moments about Q. Why not? So if I'm taking moments about Q, the reaction force now doesn't feature because it doesn't have a moment about Q, but the other two do. The 6 mg is going clockwise, and the 8 mg is going anti-clockwise. So on one side of the equation I've got the 8 mg times the distance to the pivot, which is 4d minus x. That's the distance from that force, the line of action of the force, to the pivot. And on the other side I've got the 6 mg, which is a distance d from the pivot. So 32 mgd minus 8x mg is equal to 6 mgd. Let's cancel the mg's. We get 32d minus 8x equals 6d, which gives us 8x equals 26d. Is that right? Yes. So x is 26 over 8d. Now I think, which is 13 over 4d, I think that's the nicest one so far actually. I think that's the simplest because we didn't need to use what r was. Because we happened to choose the pivot as q, that meant that the force that had magnitude r, because the line of action of that force goes through q, it didn't feature in our calculations. And that's a way that you can make these problems easier. It doesn't matter what you choose as the pivot, but if you choose your pivot as something which has a force and the line of action of the force goes through the pivot and you don't want that force in your calculations, then that's a good choice of pivot. It will help you out.